Hey folks, we're getting pretty close to starting to talk about electric fields and electric potential in AP Physics 2, which has me thinking about different ways that I can teach that and explain it virtually. And I came up with this great idea that I'm excited about, and I thought I'd share it. This is especially helpful if you use the elevation analogy to teach electric potential, which I certainly do. The modeling curriculum does if you are a modeler, right? It talks about how lines of equipotential of equal electric potential are equivalent to lines of equal elevation on a topological map. And then the electric field lines are the gradient, which is, the path of steepest descent, or the path that a test charge would follow if it started from rest. And that if it started from rest thing is key, and I think a lot of resources don't necessarily emphasize that point, or at least maybe I'm just not as good at it, or I haven't been in the past. So I hope this activity can help emphasize that point. I have my number 3 billiard ball here, which is my positive test charge. Any ball will do. I just happen to have this one. I'm excited because I believe in my heart of hearts that protons and positive charges are red. I don't know why. So I am happy that my choice in test charge is a red billiard ball, but obviously anything will work. And then I've got a large dry erase board here, which is going to serve as my potential gradient, as the ramp for the test charge. So obviously the elevation is increasing here, which shows an increase in electric potential in that elevation analogy. And now I want to draw the electric field lines, which one can teach as the lines that a positive test charge will follow if it starts from rest. So I've got my positive test charge here. I grab it, it's at rest, I let go, it accelerates down that hill. So I can draw one electric field line from top to bottom along that line. And maybe I'll use this meter stick for that later, but I just want to illustrate the point. And one more over here, and we can keep going down. And this is what our electric field looks like. So it is this billiard ball is accelerating through a gravitational field. And so we can then draw in the lines of equal gravitational potential by grabbing our meter stick then and saying, all right, where's the line along this of height 10 centimeters? Oh, that's right here. And that'll be anywhere along that line. Where's the 20 centimeter line? Oh, it's here. Maybe 10 and 20 is too big of a spacing, so maybe I need to go 15 and 5, something like that. And hopefully we see that these are evenly spaced and perpendicular. I'll bring you in case it's kind of hard to see where you're at, but we've got the lines of electric field, which run down, and then this ball runs from high potential to low potential along a path perpendicular to those lines. Equipotential lines in blue, electric field lines in pink there. All right, so that's going to be how we define the electric field and the electric potential. But then I want to emphasize that what if the ball is starting not at rest? Well, I could give it a shove, and that would be, if I shove it this way, that takes the path of a horizontally launched projectile, or at an angle. Whoa, too much, don't do that. That traces out a parabola too. I'll bring you in again so you can see that a bit more closely. And so especially if you do those types of problems where you ask them to analyze the motion of a charged particle in a uniform electric field as a projectile, I think this serves as a good example for how that can happen. Then the last thing we want to do is emphasize the fact that this is an analogy for electric fields, not the reality. There is no actual elevation difference in an electric field, so you can lay this flat and you can talk about how up here you may have a positive plate in a capacitor. Down here you would have a negative plate, and that would create the same electric field and electric potential lines. So that's my idea for demonstrating the idea behind what we mean by electric field lines, electric potential lines, and what it means to have a test charge. I should point out one more thing. which is this test charge helped us draw the lines, but these lines exist independent of that test charge. So we use the test charge as our tool to find them, but they exist without it. So I think that also serves as a helpful guide for what is the purpose of the test charge. It's what would it do if we placed it in that space, but those lines exist independent of the space itself. Hope you like that. Let me know if you have any questions or if you have any additional things that I could do with this analogy.